In this video, we will be reviewing the IR spectroscopy review questions. The first question is, which of the following will have the highest vibrational frequency? If you remember, the vibrational frequency of an IR stretch is directly proportional to the bond constant and inversely proportional to the reduced mass. So the question, in order to see which of these will have the highest vibrational frequency, will be based on which has the lowest mass. And the lowest mass is the carbon with the oxygen, which only weighs 12 grams for every mole, as opposed to the sulfur, which weighs 32, the nitrogen, which weighs 14, and the oxygen, which weighs 16. Question number 2. Calculate the reduced mass for a sulfur and an oxygen. We need to do this in kilograms. So the first thing we have to do is convert the oxygen and the sulfur into mass in kilograms. As we know, an oxygen weighs approximately 16 grams per mole, so 16 times 10 to the minus third kilograms per mole. There's 6.02 times 10 to the 23rd per mole, which means the mass of oxygen in kilograms is 2.7 times 10 to the minus 26th kilograms. Sulfur would be the same process. Which would give us a mass of 5.3 times 10 to the minus 26th kilograms. Reduced mass is M1 times M2 divided by M1 plus M2. If we substitute that in, we get a reduced mass of 1.8 times 10 to the minus 26 kilograms. Calculate the vibrational frequency of a sulfur-oxygen double bond. The vibrational frequency in reciprocal centimeters is 5.3 times 10 to the minus 12th square root of the bond constant divided by the reduced mass, which we had previously calculated at 1.8 times 10 to the minus 26th for oxygen and sulfur. We need to remember that a double bond, therefore, is twice as much as a single bond. A single bond is 500 newtons per meter. This is going to be 1,000. So if we multiply that out, the frequency ends up being 1,251 reciprocal centimeters to a ludicrous number of significant figures. Given a bond frequency of 1,700 reciprocal centimeters, calculate delta E. We remember that delta E is always equal to h nu, where h is Planck's constant, 6.6 times 10 to the minus 34th joules dot seconds, which means frequency has to be in hertz or per second. We can convert the reciprocal of reciprocal centimeters is going to give us a wavelength in centimeters, about 6 times 10 to the minus 4th centimeters. Then it's just a matter of using C is equal to lambda nu to get to our frequency that we need to calculate energy. Since we're working in centimeters, I will use 3 times 10 to the 10th centimeters per second as the speed of light. The wavelength is 5.9 times 10 to the minus 4th. That means that frequency is equal to 5.1 times 10 to the 13th, 1 over second. Now that I have that frequency, I can multiply that by Planck's constant and get to delta E. From this, I get delta E is equal to 3.4 times 10 to the minus 20th joules. Given an excitation wavelength of 589 nanometers, calculate the wavelengths of the Rayleigh, Stokes, and anti-Stokes emission for Raman, shifted by 1600 reciprocal centimeters. Pretty simple. The Rayleigh scattering is going to still be at 589. What we want to do is now calculate what are the Stokes and anti-Stokes emission. Remember that for Stokes, E out is going to be E in minus E of the IR. For anti-Stokes, it's going to be the opposite. If we take 1 over the wavelength, we get an energy equivalence of 16,978 in reciprocal centimeters. Remember, this is in nanometers, so we have to convert to centimeters. This is the energy of the input photon. If we subtract 1600 to get to the Stokes emission, we get 15,378 reciprocal centimeters. 1 over 15,378 is going to give me a wavelength of 650 nanometers, redshifted towards longer wavelength. If I look at the anti-Stokes emission, by adding the 1600 reciprocal centimeters, I get 18,578. Taking the reciprocal of that number, that means that the anti-Stokes emission, the blue shifted emission, is 538 nanometers. We have the anti-Stokes, the Stokes, and the Rayleigh, which was not shifted. Note again that we blue shifted the Stokes emission towards longer wavelength. We blue shifted the anti-Stokes towards shorter wavelength. We red shifted the Stokes towards longer wavelengths. Advantages and disadvantages of Raman and IR. Are pretty straightforward. IR versus Raman. Really, this is structural information. This is quantitative. IR has wide applicability and more structural information. Raman has higher sensitivity because of the geometry of the instrument. Remember, it uses visible wavelengths of light. It uses the vibrational information, but it detects visible light. That means we can use things like glass and quartz for our optics, glass being actually the best choice, as opposed to IR, which has to use ionic crystalline structure. This also provides greater selectivity. Draw the theoretical IR spectrum. We have to look at this compound and identify the structural features. First of all, it is an ester. It is unsaturated. It has a carbonyl. It has an ether. It has carbon-carbon double bonds and carbon-carbon single bonds. A list should include the fact that at 3500 we see an ester peak. It's usually a small peak, barely above the noise, but if it's an ester, it's usually visible. Then we have our standard peaks, 3100 and 2900 for the carbon-hydrogen stretches. This is unsaturated, and this is saturated. We have the carbonyl peak at 1700 and the carbon-carbon double bond at 1600. At 1400, we have carbon-carbon single bond, and at 1200, we have a carbon-oxygen single bond. If we're going to draw this, we're going to remember there's a small peak, a sharp peak, a bigger peak, carbonyl, just illustrating approximately how big those peaks are going to be. We apply that same logic on the multiple choice questions. Start by identifying what kind of molecules are these. This is an aldehyde. Has no double bonds, so it is completely saturated. This has double bonds, so we will see unsaturation both in the carbon-hydrogen and the carbon-carbon double bonds. It's an ester. This next molecule, again, unsaturated because of the carbon-carbon double bonds, and the OH makes that an alcohol. The last molecule is completely saturated. It is also an ester. So identify the functional groups of these molecules. Then this becomes somewhat easier to identify. This is definitely an alcohol peak, so we know immediately this has to be compound C. This has the Fermi doublet at 2700. That has to be the aldehyde, which is molecule A. If we look at this spectrum, there is no indication of unsaturation in this molecule. I don't see a CC double bond. I don't see anything at 3100. So this is a saturated system. I see the carbonyl and the ether and the little peak at 3500. This must be a saturated ester. Answer D. And the last molecule has both the indications of saturation, the carbonyl and the ether. This is an unsaturated ester. That would be molecule B. If I'm simply going to list the peaks, I can start at the end of the day. I should see the 3100, the 2900, the 1700, the 1600, the 1400, and the 1200. This says ester. Those are your carbon-hydrogen stretches, carbonyl, carbon-carbon double bond, carbon-carbon single bond, and the ether peak. All of these really can only give rise with that empirical formula to a handful of isomers, one of which is illustrated here. There are other isomers where this chain is organized differently.